Hi, my name is Ryan, and today I'm going to present my research on how highly compressed large language models as classifiers remain effective. And a shout out to my mentor, Tim. He helped me a lot with finding some helpful ideas to make the paper better. So just gonna get started. So first of all, what is a LLM? So a LLM is a large language model. It's a model, a deep learning model that has millions to billions of parameters, and it's been trained on large bodies of text until it can pretty much understand like the intricacies of a language. And it has plenty of use cases. You can use it as like a chatbot. You could fine tune it for a variety of things like question answering, classification. So pretty much they're very, very useful models. Um, but what's the downside with them? So because these models are so large and have so many parameters, including all the memory it takes to actually run these models, basically it's very expensive and it takes specialized hardware to run most of these models with parameters in the billions, such as like ChatGPT. Uh, some of this hardware is like very, very expensive, like in the tens of thousands of dollars, and this makes it pretty much inaccessible to a lot of average consumers and very expensive for these companies to run. So basically, the goal of my project was to perform emotion classification with a large language model because I've done some research and I've found out that there's a mental health crisis, especially after COVID-19, because of like the inability of therapists to match the demand from clients. So my goal was coming up with like this model that could accurately classify emotion, and that could be used for like so many different use cases. One example would be like maybe like some social media app that can automatically detect every message a user sends and then classify it. And if they show like a history of like extremely negative comments or posts or something like that, then they could be like alerted or flagged, so they can get the help they need. Or it could even be used for like a very simple like chatbot that can pretty much tell what emotion someone's feeling and respond accordingly. So the model I chose to use is called BERT, which is short for bidirectional encoder representation for transformers. And basically, all that means is that it's a model that utilizes this half of this attention block called an encoder. And this basically allows it to view an entire input both ways, bidirectionally, like in the name, allowing it to get a pretty good context for the entire message. And all I did with this pre-trained model from Google is that I added an extra layer at the end here that basically maps this embedding output from BERT, and it just makes it into it classifies it into one of six different emotions, pretty much. And I retrained it on my data set, and I was able to get pretty good accuracy with it by default without even touching it. But let's say I wanted to make this model even faster. So there's two methods I chose to use. One is called quantization, and the other one is called pruning. So I'll get into quantization first. So this is kind of a lot right here, but basically all quantization is these weights in the model that there's like millions and billions of them. This is what actually makes the model work. And all I'm doing with quantization is that I'm turning these very high precision weights. So let's say the weight is like 0.0079526 or something. That takes a lot of uh, computation to compute all these like very, very precise weights. So all that quantization does, it just maps it to pretty much a lower precision while still hopefully retaining the accuracy. And for this specific method, GPTQ, it pretty much just builds on previous methods, but makes them a lot faster. So first of all, I guess I can go through the changes that they made versus previous methods. So first of all, they found out that in previous methods, what they would do is that they'd pretty much find like the weight with like the most loss, or like uh yeah, what would cause the model to uh do the worst, and then it would focus on that first, and then it'd go in order based off of like how bad the weight affects like the final change. But basically in this new method, they found that the order doesn't really matter. And not only that, but they can actually they don't have to go row by row, which takes up a lot of time and computation power. But what they can do is they can just pretty much find like a random selection of column order, and then they can just work on the entire column at once. So that was the first big change they found. Basically, order doesn't matter, and that makes running this method on the models much faster. And the second big thing that they realized in the paper is that they can actually quantize in blocks instead of the entire layer at a time. And this basically just means that they can more effectively uh, do the quantization process on the GPU, which makes it a lot faster. So this is like a block right here, and all the model is doing is it's updating this block right here. Uh, yeah, and that this just pretty much makes it a lot faster. So it makes it a lot more viable on these large language models. And for the actual process here, all we're doing is we're going through every single block, and we're just for each block, we're looking at one column and we're quantizing it. And remember, quantizing is just lowering the precision. And after that, we calculate the error compared to the original like performance. And using that error, we update every other um, weight within the block that hasn't been updated yet. And all this does is this just reduces the loss in performance from lowering the precision of the weight. And we just repeat that for each block and then each block in the whole layer. And then for the second method I was talking about, pruning, it's much more simple. I compared two methods. Magnitude pruning is like the more simple one, and it's kind of like a baseline method. So all it does is we have the weights right here. It's like a bunch of numbers pretty much. And all this does is it finds the absolute value of the weight, which is kind of like the importance, and then it just removes the weight with the lowest importance. So here we can see the original weights are here. We calculated the absolute values, and then these are the lowest values, so we just set them to 0. And wanda pruning is a more recent pruning method that I found. It's state of the art right now, apparently, for like chatbot generation. But I was curious how well it would work on a classification model. So all this does is it uses a part of part of magnitude pruning by looking at the absolute value here. But now we actually account for the input first. So we use like a priming input through the whole model to kind of do like the initialization of the method. And here's the input into the layer, and we actually account for that as well. And we find the L2 norm, or just the Euclidean distance of it, and we just multiply them together. So first we calculate the absolute values, and then we multiply them. And once we do that, after that, then we remove the ones with the lowest priority. So it's just pretty much one extra step. And for my pruning method, I also chose to make it 2 to 4 pruning, which basically just means out of every 4 consecutive weights in the layer, 2 of them must be pruned. And even though this decreases the accuracy more, it just randomly pruning like this pretty much, it makes the speed ups a lot better. So it's pretty much worth it for the performance. And here are the results I got. So here at the bottom here, I have the different quantization amounts. So I have the non-quantized model, 8-bit quantized, 4-bit, and then 2-bit. And then yeah, and then here I was using Wanda, and I got these results. And then over here I did the same, but I used magnitude pruning instead. Oh yeah, and also just to clarify, for this 2 to 4 pruning, that means pretty much 50% of the weights in the model I just completely remove. So it really reduces a lot of the weights in the model. And using this visualization technique called TSNE, I was able to map the output of the model into this two-dimensional space. And this kind of gives me like a better look into how the model is actually doing and classifying stuff. So we can see here, this is the default model, no quantization, no pruning. And we can see it does a pretty decent job of segmenting each emotion into its own space. But you can see as we add in the other like pruning method here, then the performance decreases a little bit. They become a little bit more sparse, and same with wanda pruning. And you can actually kind of see here already immediately the loss in performance when you use Wanda pruning instead of magnitude pruning. You can see it's a little bit more spread out here, and it's kind of more like a ambiguous like blob. And here are just the visualizations for each individual thing for magnitude pruning. So this is a 2-bit, 4-bit, 8-bit, and less means the smaller bit means the precision is even lower. So this is like lowest precision versus highest precision. And actually, as like we can see, 4-bit and 8-bit look pretty similar. Once you get to 2-bit quantization, then the performance starts to really, really decrease. And moving on to Wanda, pretty much the same pattern again. As you can see, it gets more and more ambiguous as the precision goes down. And I think you can already kind of compare the visualization between Wanda and magnitude pruning here. You can see Wanda is already a lot more ambiguous than magnitude pruning. So this kind of supports the accuracy that I got earlier. And then this is the important part. This is the actual speed ups you get from doing these methods. So for a batch size of 1, meaning I only pass in like 1 input through the model without anything actually runs faster without quantization or pruning. But we can kind of see as I pass in a larger batch size, the difference starts to really show here. And once we get to like 1024 at a time, you can see there's like a huge difference. So this is my conclusion. So quantization is very effective when you're working with large batches of data here, but it might not necessarily be the best choice if you're only working with single batches of data. And magnitude pruning actually outperforms Wanda when the model is fine-tuned for classification. And actually, what I found while I was working on this is that there's not actually like much of a performance boost for pruning when combined with quantization, because most of the speed increases are coming from quantization. But there's not like a algorithm that's really supporting both pruned and quantization simultaneously. So once that's implemented, it'll make everything even faster. And also, I think my data set wasn't the best. And I think like a larger, more diverse human labeled data set, like I know I found like Google's like Go Emotions data set. I think that would work a lot better. So, yep. Thank you for listening.
Thank you, Ryan. That was fantastic. Very, very interesting, fascinating. My question for you is what is next? Like, do you want to continue exploring this research? Do you know, has it helped you refine what you might want to study in college? What now?
Yeah, so actually I kind of had the idea for this because I was working on an app with like a chatbot that was originally just using this model, but I was doing some sort of like competition and the model was way too big to fit. So basically that kind of gave me the whole idea of, oh, if I can make it smaller and run faster, then I can actually use this model in this contest. But actually beyond that, it has a lot of other uses. Yeah.
Cool. Good luck in the contest.